All right, so let's start then with lecture 5 in the course, right? Today, it's gonna be 2 lectures about feedback-based planning. First one today, it's gonna be more introductory thing, just to get the idea of what this means, right? So maybe some of you will see that you have studied these topics with different names. And then on the next lecture, lecture 6, is going to be about continuous feedback-based planning and, well, other things related. Broadly speaking, this is the summary of today, right? We are going to get back to discrete optimal planning. Although we started discussing a little on lecture 2, we will retake this and you will see that a little more on a more principled way. Then we are going to be talking for the first time about value iteration on fixed paths. And this opens the door to introducing dynamic programming and the principle of optimality. Right? So maybe these are terms that you have already heard, or you are familiar with them. But today we will give, kind of introduction from the planning perspective. Right, so there's many fields that use dynamic programming one way or another, but I hope we will motivate this from the planning perspective. And then we will explain what policy is. And then very important, navigation functions are going to be defined, and then a particular case of navigation function, which is wavefront propagation. So let's start. We want to retake like this problem of finding the optimal plan, right, in this discrete space. So this was already solved, as we saw in lecture 2 by Dijkstra and A star on a slightly more efficient way. So what is going to be new, we'll see, right? So instead of analyzing these 2 algorithms, we will start by solving all possible sequences, all possible kind of trajectories that lead on one way or another to an optimal plan, right? So for that, for explaining this idea, we will start with something that, okay, we'll see that probably it's not so reasonable, but just to analyze the problem it is, and we are going to analyze all set of constant size trajectories. So that means all trajectories with, I don't know, length 1 or length 2 or length k, right? And with this, we will be analyzing which gives like the best cost. Okay. Yes. Then, okay, as always, this is a little definition of the elements that we'll be talking about. Most of them were already presented in the first lecture 2, right? So we have now a non-empty finite state, X. Remember, this could be also a configuration space. We also have an action space. For this action space, we have a state transition function. So that means that with a given state and a given action, then we can produce an X state. Initial state, goal state, and here comes the new elements that we will require, right? Just to formulate this kind of optimality among all possible trajectories, right? The first one is we have a number of stages. That is the length of the plan, right? So here what I'm writing is the plan as this, pi, and then subindex k, indicating what is the length of this plan. And what we have here is the sequence of actions. Remember that if we have the initial state, we can generate just by calculating this sequence of transition functions. We could be calculating all state variables, right? So x2, x3, xk, and then we'll have xk plus 1. Okay. So what is this xk plus 1? This is going to be like the state that we reach at the end, or we can also call this final state, right? We don't know if this is going to be the goal state. Hopefully it will be, right? But because we don't know, because sometimes it might not be, that's why we are defining now this cost plan, right? So here we are including the cost of traversing each of these states, right? So this was an element that we have used before, right? So this is the value of edges. And then there's an extra term that is just taking into account the last state. And why is this? This is just to differentiate if the cost, this is just to capture on the cost function if we have reached the final state or not. So this function, it's just an example, but basically it's dividing, like we get a 0 value if we are in this, if we are in the sequence of goal states, right? It would be 1, or it could be like others that we consider goals, and it's going to be infinite otherwise. So that means that this plan has failed. Okay, we'll see later how this helps, but this is one extra requirement that we need. So this is all the elements that are required now to define optimal plans. Okay, so now that we have these elements, we are ready to start defining value iteration. In this case, it's going to be backward value iteration. The first step is we are going to imagine that we have a function. For now, it's not known, but this is what we are going to be calling the optimal cost to go function. What it's indicating is what is the cost given any state to go to the final state here, right? So how does, it's not, this function is depending on the index, and the index is a way of dividing the problem into subproblems, right? So if you imagine that we have length k, and it means capital K, this optimal cost to go function, what it's saying is the cost of evaluating the tail of the problem. Right? So starting from the last position, that's why we are saying this is backward value iteration. We go backward k states, right? And this is going to be giving you, it's going to be giving the cost of trajectories of length, in this case, small k. And well, formula is what we were discussing before. It's just summation of traversing all the edges and plus the final cost. So what is the difference? That here we are minimizing this. We are calculating what is the sequence of actions that is going to be giving us like this minimum cost, whatever it is. Right? So far we haven't solved the problem. We are just saying that, okay, this function exists. And well, it's going to be important like this separation. So what can we do? The most easiest thing to do at the beginning is evaluate trajectories of length 0. Okay, so length 0 means that you evaluate all possible values of final goal, and then the result, it's going to be very simple, right? It's just going to be like evaluating cost of this directly. So that means that we can generate the cost to go function of this final state simply as just evaluating this element on the cost function, right? Everyone agrees on this. So there's no magic, just 0 length. So you don't do anything. You just evaluate the value of all cost. And then there's going to be some of them that are corresponding to the goal and others that are not. So we know this point very well. Now, the thing we can do now is do another iteration, right? And for this iteration, we are going backwards. Now, instead of evaluating length, if you want here, length equals 0. So now what we are going to be calculating is the optimal cost to go for length 1. And for this, we are just going to be applying the definition. So length 1 means that there's only going to be a single edge that we are going to traversing. So that's why we are writing here just this single element, not a summatory as it was here, right? Plus the final cost, right? So here we are not doing anything so far. We are not doing any assumption. This is exactly correct, right? And the problem is solving then what is the action that gives us minimum cost, right? So we can manipulate a little, and I'm gonna try to go very slowly on this definition. Maybe you already know about it, but I'm gonna go step by step because there will not be any doubt then of what we are doing here. So we manipulate a little, and this thing that we are changing, it's just instead of using the final goal, I mean this final state, we are just substituting this equation here, right? So this equation here is substitute here, and we are also making use of the transition function, knowing that the xf, it's going to be transition of from the last this state k and applying action k, right? So we agree that just to get here, it's going to be the result of applying an action, right? So this is the only element that is not really matching. And now what we have is a function jk that depends only on this state, right? So we haven't done, we are just doing some manipulations, simple manipulations, but you can see that this actually it's a recursive form, right? So just to see, we can divide this into parts. Now, okay, here we were analyzing length 1. Let's say that we have length k, small k. We could be dividing this into parts. So the first one is, this is the draw definition according to the cost function. We are just putting symmetry and then final cost, plus we are just separating this this initial edge, right? So this was initially on the symmetry, and the only thing we are doing is separating this into parts. So because minimization is not with respect to variable UK, then we can put it outside. And what we are looking for is a recursive form, right? So we know that, well, this happens in many other domains, but if we separate things this way, like backwards, then at the end, what we can get is a recursive form that it should look familiar, right? So it's just analyzing actions from k plus 1 to capital K, and here we have another minimization, right? So this recursive form is what is known as the value iteration. Maybe you've heard about it before on different ways. You could also obtain this in continuous time, in continuous domain. But at the end, the idea is always the same, right? You have a problem, you should divide it into main problem and the tail problem. And then there's going to be this recursive form here that appears, that appears, right? So I'm just going to mark it because this is remarkable result. Just by simple manipulation, we get to here. And also remember that we need a transition function, in this case, giving us the next state, right? So the next state is just going to be evaluating this action that we want. This is the variable that we are minimizing. And then we have all the elements we require. Okay, so this, I think, gives the introduction. Now, let's see a little in more detail, right, how this is related to dynamic programming, right? The interpretation of this recursive form that we have just derived could also be explained in terms of the principle of optimality, right? And this is something that has been, well, it's also a common term here many times, but well, here we are just giving coherent explanation. So this recursive form is just a consequence of this this principle of optimality. So the definition is this: we have an optimal sequence, right? In this case, from length k, capital K, and if we have an initial state, we can determine what is this optimal state sequence. For now, we are not saying how to solve it or anything, but we are just saying, look, you have solved the plan, you have all the actions for this length, and then this is the trajectory, or this is the sequence of states we get. So then the principle of optimality, what it's saying is that this corresponding subtail problem, if you remember, it's going backwards from the end of the plan to some intermediate part, like this one, right? It's gonna be optimal. I mean, there's an optimal solution for that as well. And this is gonna be exactly the action of the sequence of actions that we calculated before. So the same, it's basically just a truncated sequence from the original sequence. It means that the solution has not really changed. Once we get here, once we get to this length of, well, k, right, then later parts of the plan could be explained, could be optimal, right? There's no need to calculate optimality all the time. So that's why we were doing, when we were getting this recursive form, we were all the time solving the subtail problem, right? And just expanding it. Why? Because the optimality is not going to change. So this allows us not to calculate things every time from scratch, but just making use of the optimal cost to go from the last iteration, calculated here, and then get a very, very efficient algorithm. Right? Okay. So this explained in discrete terms, well, is one solution, but this could be applied, as I said before, as to other domains. So here we could also be adding, like, I mean, to the value iteration, we could be adding here stochasticity and then calculating expectations or having continuous domain. But I think the most, the simplest way of explaining it is with discrete cases and you know, discrete plans. Okay, let's give a very simple example just to see how we can calculate optimal cost to go functions. Remember that this was in general the solution we get, right, from value iteration, because now the algorithm is going to be very simple. It's just going to be about calculating what is the optimal cost to go function, starting from the last position. Okay, so let me do it this way. I have here this, I have here this. Okay, maybe there's not this. And then we have all these states. The only disadvantage, and we will comment later with respect to, I don't know, other graph search methods, is that we need to search, we need to update for all state variables, and that can be a lot. But still, okay. So what about the first optimal cost to go function for trajectories of size 0? How is this going to look like? I'm going to give you like a clue. So all states are not the solution except for D. Okay, yes, I forgot to say this. Oh no, I didn't forget. It's here. So the goal state is D. So what I'm doing here is just saying, I'm going to evaluate all states. And at the last iteration, the only possible cost, there's no action to do, there's nothing to optimize, it's just evaluating nodes. The only one that gets a value of 0, because we define it this way, is only the goal state, and all the others are infinite or whatever number, right? So far this looks reasonable, right? Now let's move to the next. Oh, okay. Okay, probably not this thing. Okay, so what is the optimal cost to go for? This is length 0, and this is going to be length 1. So now what we are looking for is combinations of, I mean, all the possible length 1 trajectories that are here, that, well, they provide some cost. So we are just going to be finding which is the optimal one. So for instance, let me start here. I'm just going to write like what is the connection between nodes. So from node A, we can go again to node A with cost 2, and we can go to node B with cost 2. All right. So that means that if we follow this definition here on the forward, on the backward value iteration, what we need to do is we need to minimize with respect to the action, adding the cost of these edges, so edges here, okay, plus the cost to go from the previous iteration, right? So previous iteration is here, and I'm just indicating things with lines. And then what we have is we have 2 that is going to be this edge plus the optimal cost to go at A, that is infinity, right? So what is this? The value of this is infinity, and then the same happens for B. So why is this happening? Basically, from A, we can only get to B, and we can only get to A, right? So there's no way for us to reach the goal. So it doesn't really matter what we do for a single one length trajectory, this cost is going to be infinite. Okay, let's go to B. So B has other possible actions. I mean, all the possible actions that we can execute here is from B, we go to C with cost 1. And from B, we can also go to D, right? With cost 4. Okay, so let's analyze this. The edge here cost 1, right? So here we have 1, plus the cost to go function is infinity. So if we choose this action of getting just to C, then we'll have infinite cost. Okay, so let's see if we can do better. And actually we can. So we have an edge that is value 4, and then cost to go to reach the goal, it's 0. So this actually looks good. Oh. Okay, so let's continue. I want to do this example like step by step because you will see like well, advantages. What about the state C? So state C is connected to state D, and this edge is valued as 0, and the actions from C result in reaching state A. So here we can write it this way, right? State A with value 1. So then let's analyze what is the cost function that we can get here. So it's kind of clear. This edge 2 plus infinity, this is going to be bad. So it's basically doing this. No, you don't want to do that. But we have another solution that takes us to the goal, right? And it's this. So we have edge of value 1 plus 0. So then we have D. This is an interesting case. Just to exemplify things. I mean, here from D, there's 2 nodes that we can reach. One is E, of course 1, and the other that we can reach is C, right, with cost 1. And well, maybe some of you are saying, but we are already there, right? But we didn't say anything about stopping for now. So that means that we need trajectories of length 1 at this stage. So we need to move. We need to apply some actions, because if not, we will not have a trajectory of length 1, right? So maybe some of you are already knowing where we'll be going next, but well, unfortunately, even if we started with a solution, it doesn't mean that if we have a length 1 from here, it's going to be any good, right? So we can either go to C that has infinite cost or to E, right? So that means that here the optimal cost to go is infinite. If we start at D, there's no one length solution that is gonna reach the goal, although it's the same. So, okay, and what about E? So E is not connected anywhere. Nothing we can do. It's just gonna be. Okay, I'm gonna go a little faster now, but you see the idea. So now we get into the next iteration, and length is gonna be 2. So now we are looking for all the optimal cost to go values of plans of length 2. So that means 2 steps, just going through two nodes. So what happens here? From A, we can reach A again, or we can reach B. And actually, we want to reach B, right? So it's going to be a cost of 2 plus the cost to go function that we had before. So it's going to be 6. Right? I'm just going to indicate it this way. What about B? So from B, we could be reaching node C or node D. In this case, the cost to go here for C is 1, and the cost to go for D is infinite. So we choose this, right? We choose this one that cost 1, and then the cost is going to be 1 plus 1, 2. From this, it's going to be the same. So yes, yes, of course. So from C, we are looking for 2 length trajectories, right? And unfortunately, this is gonna look bad because there's 2 actions, 2 possible actions. One of them is taking us to node A, and the other is taking us to node C. And the cost to go from the previous iteration for these 2 nodes are infinite and infinite. So that means that here we'll have infinite. There's no possible trajectory that possible trajectory of length 2 that starts at C and ends at the desired node. What about D? So we have the same thing. We can evaluate this, and then we can evaluate this other, right? So from D, we can actually get from C. So you see here, so we'll have 1 plus 1, 2, right? And we have it. And just for you to get the idea, so if you have length 2, you can do this and then get back. Okay, I'm gonna clean a little things because later, if not, it's gonna be. Okay, let me try to go a little faster. So we have the same problem now. So A, we have these 2 actions. Oh, wait, we have a question. Should we do a parent table here? If A depends on B, it was supposed to update it. Okay, answering to the first question, no. This is the interesting thing. You don't really need, I mean, you can, actually, you can, if you do a parent table, then things are already done for you. And then undoing things is gonna be easy. But there's another option, and it's the following. Just with this cost function, with this optimal cost to go function, you can obtain what is the optimal action. Right, so from this G star function, we will be able to retrieve all the actions that are required. In general, probably yes, we want to save this just from the efficiency point of view if this is not too large, but there's the other option of just, you know, calculating them somehow, and we will explain what this somehow is. Okay, and then there's another question, but from A to B, it cost 4. You mean here, right? On which iteration, like?
Yeah, on G3.
On G3, yes. So it cost 6 because let's come here. So you first need to come to B, and then you need to go to D. So this is the only possible way in length 2 trajectories, for length 2 trajectories, to reach from A the node D, right? So that's what we are including here. This 4 is not, I mean, you could be just doing the sequence of all edges accumulated, but it turns out that for length 1, this is the cost to go function of value 4. and then you select well, this action, right? So from A, you want to go to B, and from here, you know that the optimal cost to go is 4. That is just happens to be this. Okay, if you were choosing A, then it's not good, right? Because then you're going to stay here, and then doesn't matter what you do, you are never going to reach D. Now, on the other hand, for length 3, we have another option, right? So here, what we had is that this cost was 6, but actually the cost to go to the node B is 2. And then for length 2 here, we have an improved version. So with this, we can get a cost that is 2 plus 2, 4. There's another solution that will be 6 plus 2, which is doing this. So we do this. This is one sequence, 1, 2, and 3, right? But this cost is not optimal because basically 4 is less than 8. So, okay. Let's keep going. Here, what we have is that this cost is going to be a little different because here this is this action taking us from B to C. It's going to be infinite, so this is not a good idea. We are not going to reach, and actually what we want to do is directly reach D, right? So it's going to be this. From B, we want to reach D with cost 4, so it's cost 4 plus 2, 6. C, what we have is A, that is 6 plus 1, or directly D, which is 3. Yeah, so if you want, yes, actually all these arrows, what I'm doing is just putting parents. So, but you see that parents get updated very frequently. So careful with this. From D, we have the same problem again. We have like these two nodes that both of them are infinite. So then trajectories of length 3, it's not possible starting from D, ending in D as well. And then let's do finally what is the optimal cost of length 4. Okay, yes, so here I'm just gonna go very quickly, but the optimal action to do is just stay in place because we have this option here. Here, this is gonna be this, right? So it's just gonna be going to, I mean, the action is gonna be taking us from B to C. So this is 3 plus 1, 4. From C, we have 4 here, and then we have infinite. So yes, it's gonna be 4 plus 1, 5, yes. From D, then here we have two options, this and this. So it's gonna be this one, right? So it's 3 plus 1, and then this is it. Okay, so what is the methodology for this? It's very simple. You start sequentially from the last optimal cost to go function, let's say last state, and then you slowly go there. And take a look that we didn't really calculate the full path all the time, right? So for instance, this 6, what is this 6? So this 6, what it's doing is calculating this. So the best thing we can do is stay in A. And then we know that whatever is the other trajectory, it has cost 4, right? And in this case, cost 4 of a trajectory of length 3 was this, this, and this, but we didn't recalculate this cost. It was just known that it was 4 just because of the value iteration, right? So this is a very powerful technique. Still has some issues, right? So, okay, what else? If you want, if you prefer this way, you can also redefine value iteration just to be forward value iteration. And in this case, we start in the initial position, right? And then we are just going to be counting like the cost of each action that we are taking in this trajectory. In this case, this function is called cost to come, right? And this is interesting why value iteration is called this way. So what is value, right? So in this case, value is the value of cost to come. And in the previous case, value refers to the value of cost to go. So, well, some people just use value like this. But well, here we are just going to be making this distinction. And then what? So we could be saying that the initial cost is 0 if you are in the initial state, and it could be infinite if you are not, right? And then we'll be doing the same thing, but forward. Well, only little detail is that we have inverse action, that if you remember, the inverse action was this pair of, it was the pair of state and action, right? That you had to execute just to get to this whatever desired state. Okay, let's do a 5-minute break, and then we'll get back at 4:59. Okay. Okay, we are back. Yes, we have plus. Thanks, Timur. Well, I hope, yes, we have Victor. Okay, we have Nazar. Okay, so we just start introducing value iteration in backward mode, but now let's introduce just a little tweak, a little, well, let's say technicality that will allows us to transform this fixed size trajectory optimal planning problem into infinite size, right? And um, it's very straightforward, right? So what we need to do is add a termination action, right? So this kind of a special action might not be like included in this graph, or in general might not be, but it has importance, and we'll see why, right? So then all the action space is going to be augmented. We are going to include this extra action in the case for value iteration, right? So we can always terminate. Once you apply termination, this state is going to remain unchanged. So that means that you have reached. It doesn't matter how large you do your your path. It's gonna stay this way, right? And then there's no cost being accumulated. So it's kind of keeping things, calculating things, but without updating them, right? So we are going to see now in an example later, right? So in the previous example, it was a little strange that why, if we were in the goal state, we were doing all these lengths just around, just because we had to move, just because we needed like lengths of being that size. But it's not more reasonable just to think that, okay, you have reached the goal. It doesn't really matter that you do all trajectories of some given length. What matters actually is what is the plan that is going to allow you to get to this goal. If it's of length 1 or length 100, doesn't really matter, right? But once you get there, we should be looking at that, right? And this is a little what is going to allow us to change this little the problem just a little, and results I think are really significant. Okay, so for instance, the previous example, what we will be doing is just executing the sequence of terminal conditions, right? So this is great, this is reasonable. Remember here that, in this example, we were doing like all these jumps. So I'm just gonna analyze things for D. So for D, you started here, you are at 0. For length 1, you either go here or you go to the other side. For length 2, what you had to do, the optimal thing was getting to node C and then getting back. So that's why we were getting cost 2, etc., right? So probably that was a little unnatural, but if you wanted to have trajectories of this given length and there was no way of adjusting it, that was the solution. Okay, so what is the idea of doing this? Also, the idea is that if we apply this trick, then we are going to be seeing that the optimal cost to go function becomes stationary. Basically, it converges into some solution that doesn't change regardless on how many iterations you are adding, right? And this kind of property is really, really desirable. So a little more formally, it's like this. Regardless of the iteration, the cost is going to be the same for all states. Sometimes it's hard just to define what is convergence. Maybe only one node changes, right? But still, according to this definition, you haven't really converged. But maybe that node is very important. Still, well, let's say that once we have this, once we have stationary, then there's no need to calculate for larger states. Doesn't really matter because we have optimal cost to go for all states. Okay. Yes. So then well, with this kind of optimal cost to go after convergence, then we know that this is going to be true. Right? Okay, so I hope that I have convinced you that yes, we want like this infinite length, that actually this is better for defining the problem. It's going to be a little more useful than what it was before. So let's do the same example again, but now I'm just going to go a little faster. Okay, I promise. Oh, I don't like this color. Okay. And I'm just going to be calling this g of 0, right? Because length now doesn't matter. So very interesting thing is that cost at 0, I mean, at this length of 0 is 0, and for all the others is infinite. But what about this condition that we have just discussed? So what is the best thing you can do once you're in this? So I'm going to put it here, but it's not really going to be like a big surprise. So the best thing you can do is execute this terminal condition all the time, right? Because you have already reached and cost is going to be only higher, right? So, okay, I didn't formalize like what is the cost of edges, but we assume that there's nothing negative. Otherwise, we would have infinite clicks inside this value iteration, and that will that will not allow to converge. But okay, so we have this. Now let's calculate the optimal cost to go on the next iteration. So what I'm writing here is this g of -1. And then the analysis is going to be very similar. So let's start with A. With A, there's nothing we can do. We can either reach this node or this node, so there's still infinity. For node B, what we can do is the same, just reach, oh no, wait, we can reach D at cost 4, right? So see here, yes, 4. So this is gonna be a length 1 trajectory. From C, yes, we can reach D just directly by this. This we said, let's just apply termination action because our two other options are infinite and infinite, and that looks bad. And this is okay. So let's calculate next iteration. Now from A, what we have is that optimal cost to go would be less than infinite, not by going to the same node, but just going to B, right? So that's going to be 6. 2 plus cost to go from B. B, interestingly, we are going to be analyzing all these other options. So we have C and we have D. So take a look at this. Before cost was 4. If we just of getting here, if we change slightly the length, and now it's going to be, so this is going to be length 1. But if we look for a length 2 trajectory, it's going to be 1 plus 1, right? So 1 of this edge plus 1 of optimal cost to go at C. So it's going to be 2. 1. Okay, we could be analyzing the same thing. So for C, let's take a look. For C, what we can do is we can go here. Yes. Oh, what is the other? And A. Okay, so it's either infinite or 1. So, okay, so, well, what it means is that best thing to do is just go to D. Right? And remember here that D, what it's doing is just termination action. So actually this, even if the iteration is number 2, it doesn't mean that we have a length 2. What we have here is length 1, right? So this is the only thing it's doing. Just getting from C to D on a 1 length solution, and then E that is infinite. Okay, I'm gonna do this a little faster because there's maybe some interesting examples. 6 here, What is the optimal cost to go? So probably it's better from A to go to B and then CD. So this is this length through trajectory, and this is going to be of cost 4, right? So 2 plus 1 and 2. Okay. From B, what do we have from B? That we have an action that is taking us to C, right? Of course, 1, so it's the same as before. And we have another one that is taking us to D with cost 4, right? So 4 definitely it's not better. So we just stay here. And we start seeing that, well, some of these costs are already optimal, right? We are not going to be changing them. So the same happens here. There's nothing better we can do. We are going to remain here because the best thing to do is just, try to connect with D, and D is already in terminal state. And then we have infinite. And if we calculate this for next iteration, then what we see is that we get exactly the same thing, 0, infinite. So what is this? This is convergence, right? I'm not really defining. Oh. Oops. Okay. Okay, this is 0. So we have reached cost to go function that remains the same regardless of doing more and more lengths, right? So we have discovered that the optimal cost to go for node A is cost 4, which is exactly this, right? We go to B and then CD. So this is length 3. For B, it's only 2. It's length 2. For C, it's only length 1. And then for D, it's staying the same. It doesn't matter if you try to look for larger trajectories because we have already reached this optimum, right? There's not going to be a better way for us to reach this desired goal. And this is just thanks to adding this termination criteria. If not, we were analyzing things, still you can, right? But this, what we get is from any state variable, we get exactly what is this cost to go, optimal cost to go, regardless of the length, right? We are going to be assuming that we will get there somehow. Somehow, this is a little what it's saying here, right? So once you get here, doesn't matter what is the index, what doesn't matter what is the length. And this is a very, I think this is a very good property, right? Because then we can define exactly how much, what is the cost of just reaching goal from any state on a very efficient way, by the way. So, okay, now with this, we are ready to redefine what a policy is, right? So we have now phrased this idea of, well, how to calculate value iteration for infinite plans, which gives us like this optimal cost to go from any state. But in addition, this is what I think Mark was asking. Do we really need to save parents? No, it was Timur, sorry. Do we really need to save parents, or maybe with this function we can still calculate what is the optimal action? So indeed we can, right? We just need to apply this formula or apply this equation, minimize this equation where we have a function, right, that has already converged. It's not going to be changing. And then we are analyzing all possible actions that could be applied. So just by doing this, looking at what is the best cost, basically, if we come here, it's like saying, okay, you want to calculate what is the best action for your, for instance, for this state variable, just to get there. So then what we do is we apply an action, and then we see that best action that is minimizing this cost is going to be taking us to the state B, right? So this is the optimal action just by solving this little problem. So we don't really need to solve, you can, right? So it's going to be more efficient, but just analyzing all possible actions. And maybe the action space is not going to be that big, right? So state space, yes, we agree. If you had agreed, it's going to be large. So analyzing this can take time, but analyzing all possible actions for a given state is not that much. So still, that's a very efficient way of calculating it. There's several forms of this, so we are just presenting discrete case, but there's also continuous case. And then this is also very interesting because now we can define the term policy, right? In this case, it can be a function. If you have like finite number of states, we could also be just doing a table. But what this function is doing, I mean, it's this function, it's nothing else, is giving us for each state, what is the optimal action to apply, right? And this is also very good. It's ideal case because we don't have an idea of the plan, but we don't care. We just follow dynamic programming and value iteration algorithm, and it's going to be giving us all the time the optimal action to execute. And we know that this is going to be the plan. We don't know, we don't care too much. We are just going to be sequentially calculating this, and we have guarantees that this is going to be optimal, right? It's this action we call optimal because this is generating the optimal sequence of states. So this is great news. This is what means really a policy. Allows to calculate actions from any state just by doing this, well, minimization of a single step. And this is also very powerful, right? Because now it's not just that we have calculated a plan from an initial position to a goal position. We have a tool that allows us to calculate a plan from anywhere to the goal position. And yes, this is I think this is really something to think about, because before the effort was just to creating a path, a single path, and then you needed to build this structure, but now we can get from anywhere to the desired goal. Not just that, not just we have the cost, but we can also calculate the action, right? So yes, we have optimal action to execute, and as we have discussed, the sequence of a state is going to look like this. You have a transition function, you have your current state, and then you have your optimal policy. And this is just going to be recursively calculated until you reach the goal, right? So this is kind of amazing. This is actually the power of a policy. Once you have calculated it, and maybe it's a little complicated to calculate it because, I don't know, your state space is large and calculating this value iteration might take time. But after convergence, you have like optimal policy calculated. Okay, so how does it look like? Basically, we have this goal here in this grid world, and we are going to be applying value iteration, right? So remember, at the beginning, we are going to have like this, then this optimal cost to go function. We are just increasing the number of iterations, so on, until convergence, right? Until we get just this. And once we have the optimal cost to go function, we just apply the minimization, or maybe we save a table, and then what we get is a result like this. So all these are actions here. What we are, it's basically going up, going to the left, going down, and I guess going to the right, right? So we have this set of actions, and for each state, we know what to do. So what it means that you start here and you just follow the policy. There's nothing to think about, just follow the policy, right? Here, 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 and here. And this is another interesting thing. What happens if, for whatever reason, and we are not talking about noise, what happens if you wanted to come here, but you end up here? I don't know. Intuitively, yes, this is noise, but we haven't really talked about perturbations or noise. We will later. But the great thing about policies is that without explicitly defining noise, or taking into account how propagation of states looks like, if it's like deterministic function or some probabilistic, it doesn't matter, because now we still have a plan. We just follow the policy, right? So whatever it is, we just follow the policy. And it looks like a no-brain solution, but yes, this is just thanks to dynamic programming. So, well, I hope that with this, the idea of this technique is powerful. Is now like, well, I think you all agree with this, and we'll see a little more cases of this, right? Let me comment a few things about Dijkstra revisited. In some form, it was dynamic programming, right? But what Dijkstra algorithm was doing is a very clever way of applying the dynamic principle, dynamic programming, sorry. Right? So how was that? How is that possible? It was possible because we were distinguishing, right? When we have in this table, we have infinite values here. Why are we calculating them, right? So why do you want to calculate infinite and infinite again? So probably this doesn't take you to any good place. So what Dijkstra is doing is just doing a clever way of considering these not visited states not worth of evaluating, right? So you don't check them, you know there's not going to be a good solution, it's going to be bad whatever you do, so you are good, right? You are not wasting time just doing this well, kind of useless checking, right? If, I don't know, your neighborhood has not been explored and you have a lot of very high cost, so it's not gonna be of any use. On stationary states, when these values don't change, Dijkstra what does, it's consider them as visited, considers them as dead. It's not checking for them either, right? So the algorithm knows that some states here, the value of these states are not going to change because there's nothing connected to it. And it's not worth it evaluating them again, right? So there was this other thing going on, not just like checking if they were saved or not, but the only thing that worth evaluating is these states that have some promise of taking us somewhere or optimizing or improving cost to go on the nervous region. And that's why we were using a queue, right? So on the queue, we were just putting all these values. Once we evaluate them, there's no need to re-evaluate them. You can still, find other paths and just do this duplicate solution. But you don't need to evaluate many of them. You don't need to evaluate them all the time. So only those that are on the queue were considered to be giving an update on the cost to go function. And that was the reason behind this efficiency. On the other side, well, let's say that yes, the algorithm was just designed to do kind of a single query. So from one initial state to a final state, although you have like optimal paths around, but we are not giving like a proper cost to go function. It's only evaluated in those regions that we wanted to explore to get to the goal, right? While value iteration is evaluating all states. So in this sense, well, yes, we have more information, but maybe you can just keep, calculating Dijkstra for all values and then still get like some values. Then why are we using value iteration? Why am I talking about value iteration at all? Right? If Dijkstra is so good and so efficient. Well, unfortunately, this queue that is easily explained for grid-based scenarios can be a little expensive, right? If you have like expensive means there's going to be a lot of states, you are going to be adding a lot of elements, and there's not a clear structure. So sometimes it might be more efficient just to do value iteration, evaluate all the states, and that's it. Instead of calculating a very strange cost and then updating things and removing them. So this, of course, requires like higher dimensions. For few dimensions, it's like probably no need. But well, depending on the case, keeping this priority queue does the trick, but it's not so efficient. Value iteration is also an algorithm that could generalize well to continuous state spaces, continuous time, stochastic optimal planning. So there's many follow-ups of just applying the principle of optimality, right? That are not only for discrete cases. So discrete cases is the way for us to introduce them for the first time, but it's not the only one, right? It's gonna appear these many other places, right? So I think, yeah, well, I think originally, or the better way of describing them is by discrete cases, but do we have Dijkstra in continuous spaces? Do we have Dijkstra? No, right? So, well, this is another limitation. So we need to be a little more general, and well, for other kind of problems with noise or whatever, then yes, value iteration is a very powerful tool, as I was saying. And well, this is a little note that I'm not going to explore much, but Dijkstra also belongs to this family of algorithms that are called label correcting algorithms. So what is this? You have a plan. In this case, well, whatever Dijkstra has searched so far. And then what we do is modifications of this current plan. This is, I don't know, evaluating next element on your queue, right? So what you are doing is little updates to your plan. You are not searching over and over again for the full solution. Right? Value iteration is doing an iterative form, but still it's evaluating all the states. But Dijkstra, we should take it as if you were doing small increments on your plan every time, right? And then you try to improve your plan every time. So this is actually another, well, kind of approach, I would say, for it's better suited for these logic-based problems where we have like state spaces that are very large. It's very hard to evaluate all of them with, I don't know, doing graph search. And then what you do is you basically, instead of trying to solve full problems, you start with an initial condition and then you start changing little things. I don't know, maybe they are integer variables, some long process or whatever. But it's just small changes that you are doing. And at the end, you are going to end up with a solution, right? So yes, as I was saying, yes, combinatorial problems actually are a good example of this. So yes, we have 3 credits, so I'm not going to get too much into this, but just for you to know that, okay, there's a way of looking at Dijkstra as a way of value iteration with clever tricks, or maybe as this label correcting algorithm, right? Where you have a plan and you update it little by little with these new candidates, and then finally you get a plan. Okay, yes, other remarks. We haven't talked about uncertainty, but on this example, I already motivated this robustness to perturbations, right? That is implicit on policies. So because you can solve from anywhere, from any state to your goal, that makes you kind of robust to uncertainty. So as long as you know what is your state, you are good. If you don't know what your state, then that's an extra level of uncertainty that, let's say that it's not so direct to solve. But still, this is great. And we haven't really talked about uncertainty, and we're robust. So, well, yes, this is a great feature. Okay, so this was like the example on figure. Okay, yes, so from anywhere, disturbances are helping. Okay, what is this other remark? That dynamic programming and value iteration would be taken to infinitesimally small discrete spaces, you know, like very small resolution. And this could be considered like continuous state spaces, right? You could also be considering here time or continuous time transition functions, remember, basically how to change the state over time. So it could be applied very easily. And here it's just this motivation, but easily to other domains. So just, well, as I said, this is going to be appearing again later. And also it includes random variables. So, well, these are great features. We'll see later, but maybe for today, it's not necessary to describe them more. Okay, now let's describe what navigation functions are, because this is also, I think, one of the key components on planning. So, okay, we have described value iteration, which maybe some of you were familiar, but now let's get to the interesting things that are affecting on planning. right? And it's just these navigation functions. You will see the relation. It's not the same. It's just related, but it's not exactly the same. So for this, let's consider a potential function. Remember that this x is discrete state, right? And from any state, what we get is a real number, a value, a positive number, right? So this is what this potential function is doing. We'll explain again on next lecture about potential functions, right? So then what we can do is we can define a feedback plan. Remember, feedback plan is this, well, where you have like basically actions just calculated by your state in terms of policies. And we can define just a very simple feedback plan. It doesn't mean it's optimal. We don't know this for sure. With the use of this local operator, right? And what is this local operator? Well, is this function here. Intuitively, what it's doing, it's just selecting the next action that reduces the potential, right? So you can think about it kind of a greedy approach, right? So it's just trying to minimize. We don't know what this potential field is, potential function is, but let's say that, okay, you have it. And then how you are going to be calculating function, how you're going to be calculating actions, it's just by minimizing this potential. And what we can do now is slightly change the local operator, and we are going to be adding this term. Okay? So now this equation here should be very familiar, right? And I'm just going to go back a couple of slides here, right? So what we have is that this was our definition of optimal action just by the after calculating the cost to go function after convergence, right? And now what we are doing is a slightly different thing. So we are just saying that we are going to be calculating actions if we have a potential that we don't know what it is, but this resembles actually the value iteration, right? Or what in this case, calculation of well, actions just by this. So if this potential function was the optimal cost to go function, then we will have exactly value iteration. I mean, well, no, not value iteration. So this is a feedback-based plan, right? So here what we have is, I mean, value iteration is how to calculate optimal cost to go. And with this, what we get is we get the plan. We get what are the actions to evaluate. So what is the interesting thing about this? That maybe we don't need to calculate optimal cost to go function. Maybe we just propose a function that is similar, right? And now we are going to be discussing exactly how this looks, how this should look like, right? But because, I don't know, maybe the optimal cost to go, it's very expensive to calculate. So this is a way of calculating a surrogate of it. And still what we want is to have a plan, right? Remember that here we were discussing about optimality, but a plan, as we were describing at the beginning, is just a sequence of actions that takes us to the goal state, right? So, okay, this is the first remark. There's many potential functions that are useless. So why they are useless? Because they are not going to solve the problem. And what you want is to solve the problem. So now there's going to be this relation with potential functions and navigation function. So the ideal case, imagine that someone just proposes a potential that has these characteristics, right? It starts at 0. I mean, no, it has value 0 when you reach goal. It has value infinite if you cannot reach the goal, right? So this is very important. The same happened on optimal cost to go. We had infinite values when we couldn't reach the goal at all. And then what we have is that for all states, this local operator should improve a little the state, right? So whatever you do later, it should be a little better in terms of this cost, a little better than before, right? So if you assume that there's all actions have cost, right? There cannot be like negative values or things like that. Then potential function should have this property that you always improve this. So if we have these conditions, then what we can call is this a navigation function, because then the potential it's gonna be guaranteeing that you are gonna reach the goal, right? So this is very interesting. Some of these potential functions are actually navigation functions, and then the idea it's the simplest thing, same as before. You just have a policy that you calculate, well, calculate like this. You are given, I don't know, maybe because someone calculated or because you have analytic function or whatever it is, you have this potential, and then you are just applying the sequence of actions. And you know that if you have like some properties, then this is going to be a navigation function. It's a valid plan. It's not optimal, right? If it was optimal, then, well, we know how to calculate this. So potentially it's calculated by valid iteration. Okay, what are other options to calculate this potential field? So I was talking about Dijkstra before. So this is another way of calculating this. You just have Dijkstra, and then you construct this optimal navigation function. Any other forward search methods that we were discussing in lecture 2 should be fine as well. So maybe they will not be optimal, but still they will take you, they will give you like these qualities. So values, cost, it's basically evaluating cost, right? So you have 0 when you reach the goal, and well, any other cost for other states. Okay, so yes, and maybe you don't construct them, you just imagine them because you have analytic functions, and this is going to be for next lecture. Okay, I'm going to do just 2 more slides and we'll be finished for today. But let's see a very, very simple application of this navigation function, because we started with this more general idea of dynamic programming, value iteration, but then at the end, how this translates into things that are useful, right? So wavefront propagation, it's a particular case of an optimal navigation function, and optimal is on the sense of length of the path. And it's also a simplified case of the Dijkstra algorithm. So this is great because we are improving Dijkstra with just this wavefront propagation. So what is this algorithm doing, right? Basically, we are not considering here any cost. We are just considering that all costs are unit cost, right? And this is the idea of you're just measuring length, right? So cost of one is just moving from one state to the other, like from here to here, right? So here, cost is just changing from 1 to 2. So when we do this, when we calculate cost just to be this way, if you remember from problem set 1, there's going to be on the queue many, many new states, like for instance, this thing, right? So at the beginning, we are going to have 4 states that have the same exact cost, right? So what we were doing is we were selecting one, and then we were doing all the parts of the algorithm. But the thing about wave propagation is that it's exploiting the fact that because these costs have the same, you are just going to be writing the cost of each of them, right? So you know that the cost, the optimal cost is just traversing this, and then you evaluate all of them at the same time, right? You don't need to, evaluate one and then the other and then the other and then the other, right? Because this is what we were doing when costs were any cost, right? So that's why we had the priority queue. Now all of them have the same priority, and the optimal function is going to be very clear. So there's only one, and it's going to be like, look, you have traversed one state from this initial state to the next one. Therefore, the cost is going to be 1. There's no other way. There's no other way that you are going to be getting less, right? So with this, you can eliminate states very easily. And then you just do this kind of wavefront propagation. So if you think about it, you start with length 1, then you go for length 2, right? And then you keep propagating things. So this is what is happening here. 3, 4, 5, 6, 7, 8, 9, 10. You see it, right? And then you just keep propagating. And then here, yes, you have 12. Here we have 13, 14, and so on. So it's kind of something that is expanding. Imagine water falling from the sink. It kind of propagates, and this actually improves the Dijkstra algorithm. So you don't need to evaluate so many things. The only problem is that this only works for optimal cost of length. Right? It doesn't work if you have strange cost. Okay, so another example of very interesting way of calculating this potential. In this case, well, yes, with this we'll get like a cost for each of the states, and with this we can calculate the U star just with the arc mean, right, of L plus 5. Okay, well, I'm losing parts here, but well, just put transition function and all this. Okay, another example, very famous example of navigation function is what is called the maximum clearance, right? Just going to explain intuitively what it is. So we start with some obstacle. Okay, let's say that we have here xi and here we have xscope. Okay, and we have here an obstacle. So the idea is, okay, maybe yes, maybe let's add another obstacle. Okay, so the idea is that we do wavefront propagation from any state to the boundary with the obstacle region. So what does it mean? Instead of propagating initial state, we propagate the boundary of the state region. So imagine we are doing length 1 and here length 1. Okay, and then we do the same for length 2. We basically do wavefront propagation of all these state heres, and then I don't know, let's do this again like this. And okay, yeah, there's no more things to propagate. I mean, technically, yes, we can propagate things, but then what the algorithm is doing is that as waveforms propagate, they meet approximately at the maximum clearance point. And this is what I was writing here, right? So we have, this is the clearance point. So we have here, remember, this is discrete state variables. Here, okay, here we don't know, so we should keep calculating things here, and then maybe they meet here. Okay, so this should be the maximum clearance, right? Let me try to do this well. Okay. Okay. So we have maximum clearance. This is the maximum distance, possible maximum distance to obstacles, right? So remember that A star always, or Dijkstra always provide a solution that touches objects. So this is not very comfortable, and actually it's not very good, right? Depending on what problem you have. And with this, what we have created is skeleton state of variables that are on this maximum clearance position, right? So then what we do is step number 3, add the goal into the state S. So the goal, okay, let's say that we add it here, it's a little different. And we try to, oh, okay. Yes, okay. Because this is a navigation function, we'll have initial state, but maybe we don't have initial state. So it should be from anywhere to anywhere, right? So here we are just starting. And now imagine that we start here at this position. So the second step is yes. Second step is from any point, we need to connect this to this skeleton state S, right? So it's also going to be maximum clearance or whatever you want to use. And then once you have this subset of states that are only the skeleton, then you do graph search over S, right? So here I'm just writing S. So why is this? Because you don't want to analyze things that are here. You just want to analyze things that are on the maximum clearance path. So it's kind of, you find a path, you try to connect to the path, like for instance, in this way, and then you are just doing standard graph search. This is also proved to be a navigation function, because then, for instance, this could be your initial state. This is number 2. And then you just do the same, right? So you just connect to state S and then do again graph search over this skeleton. So, well, this is another example of discrete navigation function. These two, I think, are the most popular ones, Wavefront and maximum clearance. It's also known as navigation function 2. And yes, this is all I wanted to discuss for today. There's a lot of topics. I discussed a lot of new things maybe for some of you today. So feel free to ask, write comments in Telegram or in Canvas or whatever you want. And yes, that's all I have for today. Is there any comment or question, something that maybe I can cover again?
Yes, I have one question. This maximum clearance algorithm, is it differs from just taking the average between the obstacles? Seems like it's similar to that. Because the points when the wavefronts will meet.
Yes.
Maybe.
This is obstacle 1. This is obstacle 2. And this is obstacle 3. Now you do the average and you're in a very bad spot. So for 2, yes, but this generalizes to any kind of obstacle. So as long as you do wavefront propagation, and this is something that I do in discrete maths, right? But which states are we taking here on the boundary of C obstacle and C free, right? So it has a little more technical details, but no, averaging is not a good idea. So you want to do wavefront propagation because this is the only guarantee that you are going to have that this is exactly the midpoint between the closest obstacles, right? If there's a third obstacle here, I don't know, obstacle here that propagates, but it's not really affecting how these two meet, doesn't matter, right? Because it only matters when the first two wavefront meet. It doesn't matter if the third one meets later, right? So if there's a third one that meets, it doesn't matter because you have already created your set skeleton S. Yeah. Okay. Then I will see you next week with kind of continuation of feedback-based functions, explaining even cooler things now on continuous spaces. So today was a little introductory to some of these concepts. That's what I wanted to make sure that these things are clear. And then we'll move to a little, I think, yes, more interesting or more useful topics that we can apply in planning. Oh, stop share. All right, then, thank you, everyone.
I'm sorry, am I able to discuss